of humanity. Okay, the reason is so this problem over here. Now, if you try to do this problem, let's say just in the way that we do commonly. So first of all, let's say you may want to find the first derivative, which is e to the power x cos x plus e to the power x sin x, e to the power x common sin x plus cos x, and you may again want to differentiate this, right? D square x of dx square. The thing is, it becomes complex with time. The now second derivative will be e to the power x times minus just cos x minus sin x. So this will be e to the power x times 2 cos x, right? Now if you go on, also it may not be obvious what the pattern might be for the nth derivative, right? So yeah, so in this scenario, if you want to find the nth derivative, like going this way might be a hard thing. So what we will do is we will try to introduce complex numbers and make this a really easy problem. So let's see how. So first of all, we do know that the e to the power I theta this is the Euler's formula, cos theta plus I sin theta, right? So from here we do know that cos theta is just the real part of e to the power I theta, and sin theta is just imaginary part of e to the power I theta, right? Yeah, we will use these facts. We want to find nth derivative of e to the power x sin theta, right? Sin x, right? Now we know that sin x is just the imaginary part of e to the power ix, right? I can also move the another e to the power ix inside the imaginary part, right? Because like that will not, even if it goes inside, it's just a real thing. So the imaginary part will not just change. It's just like the constant multiplication. I can also take the imaginary part outside the differential operator, right? I can do that too. D dx, this is power, this is power n actually, dx to the power n. So this is n of e to the power x times I plus 1. Okay, now you can see that it's in a real simplified form. And we do know that if we want to find the nth derivative of e to the power ax, so what happens is just this a will come forward n times, right? So that will be e to the power n times e to the power ax. So we can use the same thing now. It has become too easy actually, yeah. So we'll have I plus 1 to the power n times e to the power x times 1 plus I, right? Now we need to find its imaginary part, right? So first of all, we will try to take these complex numbers to the Euler's form again, so that from the Euler's form it's easier to separate the real and imaginary parts and just get the imaginary part. So for that, I will first of all try to like divide both of them by root 2 so that they become cos theta and sin theta. It's just the same as multiplying by the hypotenuse, considering 1 and 1 as perpendicular in base. And so I also need to introduce 2 to the power n over here, right? And this is e to the power x times e to the power ix. I'm just trying to separate the real and imaginary things. So imaginary part of this is root 2 to the power n, or root of 2 to the power n times. Now this is just cos pi by 4 plus I sin pi by 4, right? To the power n, e to the power x, e to the power ix, right? So now this will be imaginary part of root of 2 to the power n. This is just e to the power I pi by 4. So this is e to the power I pi by 4 times n times e to the power x, e to the power ix, right? So this is now imaginary part of square root of 2 to the power n, e to the power x, e to the power I times x plus n pi by 4. Okay, now all these are real things. They will just go out of imaginary part like some constant numbers, right? And now we need to find imaginary part of this expression, e to the power I times x plus n pi by 4, right? So now we know that for e to the power I theta, the imaginary part is just sine theta, right? So for this case as well, the imaginary part will just be sine of x plus n pi by 4. And that is the answer. See, so we got a general expression for any powers. If you wanna check, then yeah, this will definitely work for any powers. So if you wanna check, we're taking n as 1. So we get, if we take n as 1, we get square root of 2 times e to the power x times sine of x plus pi by 4. Now this is sine of x plus pi by 4 is sine x cos pi by 4 is 1 by root 2 plus cos x sine pi by 4 is 1 by root 2 e to the power x sine x plus cos x. Yeah, math works, guys. Math will never give us wrong results, right? Again, if you take n equals to 2, it will definitely work, because I'm pretty sure that maths can never fail, because maths is maths. Now this is just 2 e to the power x sine pi by 8 plus x is just cos x, which is what it's over here. So yeah, this generalization might not have been obvious to us, right? If you had just seen the numbers. But yeah, we were able to solve for general expression due to the complex numbers, and that's why complex numbers was really helpful for us. And yeah, of course, it's the best friend of humanity. I hope you loved the example, and I hope that you will also use such examples in your other real life maths too. And I think this will definitely be helpful everywhere. So that's it for today, guys, and look forward to seeing you in the upcoming videos too.